So I'm Ehsan Karim. I'm an assistant professor in data science in the School of Population and Public Health at the University of British Columbia. I am also a scientist at the St. Paul hospitals. So the area of research that I'm really interested in is causal inference as well as data science topics. So these are the materials that I will talk about during this workshop, and this material has been divided into 10 different pieces or chapters that I'm going to talk about. And at the end of each chapter, and don't worry, these chapters are not that big. At the end of each chapter, I will pause and try to get a sense of whether you have any question, and then we can discuss about those questions before moving forward. General idea of this workshop is we are going to talk about propensity score matching in particular. And the way I will present these materials is that at first I will talk about the basic terminologies that I'm going to use throughout the workshop. And then I will introduce the propensity score. I will talk about different steps or stages of propensity score. And then I will talk about a scenario where propensity score matching might be favorable compared to a general regression matching. Sorry, a general regression analysis. I will also talk about some of the reporting guidelines. For example, if you are doing a propensity score analysis and you are trying to publish, then what are the key elements that you need to have in your article? And then I will have a final discussion about some of the benefits and the limitations of the propensity score analysis. So throughout this workshop, I will be explaining some of the data analysis aspects of the propensity score. And for this analysis, I will be primarily using R. But if you are not familiar with R, that's not necessarily a problem, because I will be using the analysis outputs as a way to explain what we are trying to do and what are the things that we should expect in each of the steps. But that does not necessarily mean that you need to understand or know what is R or how the R really works. Let me dive into the useful terminologies that I will be using throughout this workshop. So I will spend a bit of time explaining some of the concepts that will help us understand various steps of the propensity score analysis. So before defining what is it that we are trying to estimate, let me give you a very brief introduction to the potential outcome framework. I can make the font a bit larger. Okay. So in this potential outcome framework, here are the notations that I'm going to use. For the treatment or the exposure status, I'm going to denote this as A. For the outcome, I'm going to denote this as Y. And for the confounder, I'm going to denote this as L. So the particular example that we are going to use for this chapter 2 is this treatment is binary variable, where, say, for example, the treatment is a cholesterol reducing treatment known as rosuvastatin. So we define A equal to 1 when a person takes rosuvastatin, and we define A equal to 0. That means that the person does not take any rosuvastatin. For the outcome, we are defining total cholesterol level, right? So this is a continuous outcome, and we are going to define potential outcome when exposed as y, and in notation I have a equal to 1. That means that whatever cholesterol level a person should have when a person is treated, right? And I will go through a definite example a bit later of how I'm defining it. And the potential outcome when a person is not exposed, the outcome is then denoted as ya equal to 0. And I'm using L as a confounder in this scenario. So the general idea that I am interested in the effect of this treatment, rosuvastatin, on this outcome, total cholesterol level. And there might be other variables such as this L variable, which is basically at this point a risk factor for this analysis. But later we will talk about what happens if this L is a confounder. All right. So there are three types of parameter that I'm particularly interested about. The first parameter is treatment effect of an individual. That means that the rosuvastatin that a person takes, what is the effect of that treatment on one person? That is known as the treatment effect for an individual, or TE. But generally in public health, we are not necessarily interested in only one person. We are generally interested about a group. So instead of talking about a treatment effect, we can think of an average treatment effect for the entire group. So in general, that is known as the average treatment effect, or ATE. And the last one that I'm interested about is that the person who take rosuvastatin, what is the effect of that treatment on the treated? And that is known as average treatment effect on the treated, or ATT. All right. So these are the three parameters of interest that we are going to be estimating. Let's start with the first one, the TE, or the treatment effect for an individual. All right. So for the treatment effect for an individual, let us assume that we have a subject. So for example, this subject could be John, who takes rosuvastatin. That means this person's A is defined as 1 because this person is taking rosuvastatin. His total cholesterol level is 195 milligram per deciliter. Right? So this is the potential outcome for this person when he takes the rosuvastatin drug. That is why we are defining this as potential outcome Y with A equal to 1. All right. And then think about a scenario where we again follow up this person John, but this time we are not really giving this person any rosuvastatin drug. So that means that we're following up this person, but this person does not have any rosuvastatin. So we keep following up this person, and at the end of the follow-up, we get 245 milligram per deciliter at the end of the follow-up. And then once we know the effect of this drug under treatment is 195 versus effect of this drug when not taking the drug is 245, we can estimate the treatment effect as the difference between these two quantities, the potential outcome when he took the drug, the potential outcome when he did not take the drug. So just by subtracting these two, we can get a minus 50. One thing to note here is that in a realistic scenario, we cannot really observe the same person under two different treatment conditions, right? So we cannot just get the treatment effect under treated and treatment effect under not treated for the same person in the same timeline. For that, we would need to invent a time machine so that at one timeline, we give the person the rosuvastatin drug, and in another timeline, we do not give the person the drug, and then we could estimate something like this, right? So this treatment effect for an individual is entirely a hypothetical concept that we are trying to explain, so that we can build upon this definition to make a definition that we can use in a real world. Let me move on. And throughout this document, you will see some of these R codes. If you do not want to see the R code, you can simply hide global, and that will disappear, but I'm just going to keep them for now. All right, so the next concept I'm going to use is the average treatment effect on a group. So imagine now that instead of just one person, I have 5 different persons, and I follow them up and try to see what is the outcome at the end of the follow-up for each of this person. And again, say for example, I have a time machine and I go back in time, and this time I do not give these persons any rosuvastatin. And then I observe all of these outcomes for these subjects. Again, similar to John, everyone has a potential outcome under treated. Everyone has a potential outcome when that person is not treated. And then we can estimate the treatment effect on each of these individuals. So for example, on John, when he takes the drug, that treatment effect is -50. But when Jim takes the drug versus do not take the drug, the treatment effect is -60. So on an individual level, it is possible that the treatment effects may vary. But the way we are trying to estimate this average treatment effect is basically by averaging all of this treatment effect for the individuals. So we are just going to average all of these numbers to get the number -58. So that would be our average treatment effect for this particular group. Right? All right. So how do I really interpret this average treatment effect? The interpretation is that if I had everybody in the group treated, we would have certain amount of total or the mean potential outcome under treatment. And we can also have mean potential outcome when the persons were not treated, right? So notice that we are not really separating out the groups. There is no case or control type of scenario. Here, everybody is treated and everybody is not treated. So that is the interpretation of the average treatment effect, that if we have the entire population as treated and knew their potential outcome, and if we had entire population as untreated and knew their potential outcome, we can simply take the difference of those and make an average out of them to get the average treatment effect. So again, this average treatment effect idea that you are seeing is a hypothetical construct. In a realistic scenario, in a real world, you cannot necessarily estimate an ATE unless you are using some sort of statistical technique to estimate this. To understand this better, one strategy that you could employ is a design known as the crossover design, right? In a crossover design, you give everybody treatment and then there is a washout period, and then you give everybody a placebo, and at the end of it, you can estimate the average treatment effect. But in this particular design, I'm not necessarily talking about any crossover design. I'm just talking about a scenario where we have a time machine where we can see the potential outcomes under treated versus untreated. and then we can estimate the average treatment effect. So this interpretation is important to recognize because in a general study, when you are trying to estimate, you cannot directly estimate the ATE. For that, you need to have a somewhat better design to think about how can we estimate this treatment effect from a realistic population. All right. So in the propensity score analysis, the way we do the analysis, it comes from some derivations of mathematical formulas, and those formula relies on some assumptions. So some of these assumptions that we are using to estimate ATE from a realistic study is that we have exchangeability, positivity, consistency, and no interference, right? So what is exchangeability? Exchangeability is something, and it is helpful to think about clinical trials to think of these particular assumptions. In a clinical trial, when we do a randomization at the very beginning, we are not really choosing which patients we are going to give the treatment. We are randomizing it. We are simply tossing a coin and trying to determine which person is supposed to get the treatment. And then we are again tossing a coin to determine which person is going to get the placebo. So there is no way there would be any introduction of bias in this type of analysis because we are not really choosing a person. One example could be, say, for example, in a hospital, when a patient wants a drug, then the doctor tries to determine whether this person really needs the drug or this person is young enough that that person may not need the drug. Say, for example, if a person is asking for a drug and doctor says that, oh, you are too young, so you do not need to take this drug, you can just walk it off, whatever problem you have. Or if a person is of older age and this person is frail, this doctor would be tempted to give this patient a drug more quickly than a younger person. So in this particular example, this age would be a determining factor of whether a doctor is willing to give that patient a drug or not. So in that scenario, this exchangeability assumption would be violated, right? So what we're trying to establish here, whether we have two groups of people treated and control, but before giving them the treatment at the baseline, when we are separating out these groups, whether there is any systematic difference in these groups. Obviously, when we are collecting data from a hospital with a person who got the treatment versus who did not get a treatment, these people might be different in a hospital setting or in an observational setting. But in a randomized clinical trial, when we are determining who gets to be in a treated group versus who gets to be a control group, we generally randomize it. So there is no reason of bias of why a person is getting a treatment versus why a person is getting the control or the placebo. So in that scenario, the exchangeability assumption would be violated if there was a reason for the doctor to prescribe a patient a drug. All right, the second assumption is the positivity assumption, and this positivity assumption says that there has to be a non-zero probability for a person to get the treatment. And this probability cannot be 0, and this probability cannot be 1. That means it has to be in a scenario where the patient is eligible to get the treatment or no treatment. Either is possible. If it is a scenario that the patient must get the treatment under the condition the patient is in, then the patient would not be, or the scenario would not be following a positivity assumption. Right? So think about this. When there is a non-zero probability and the probability cannot be 0 or 1, then both of the treatments has the possibility. So the patient has the possibility to get both of these treatments, either treatment or the placebo. All right. So the third assumption is the consistency assumption. If we are trying to estimate the treatment effect of a treatment, we need to determine which treatment it is. Say, for example, I have a 5 milligram treatment and I have a 10 milligram treatment. I cannot just give some people 5 milligram and some people 10 milligram, and at the end of it, we average the treatment effect. It does not work that way. Then, say, for example, if I give a patient 5 milligram, if I give another patient 15 milligrams, say, for example, what would be the treatment effect? What would be the treatment for which we are seeking this effect? Is it 10 milligram then? No. So we need to determine whether it is a 5 milligram treatment or a 15 milligram treatment. And if it is a 5 milligram treatment, then we just give 5 milligram treatment to everybody to determine what is the effect of this 5 milligram treatment. We cannot just have different versions of treatment in the treated group. Obviously, we can have treatment and placebo, that's fine. But within the treatment, we cannot have many different versions of treatment. All right. And the last assumption is no interference. That means that if the doctor is prescribing a treatment to a person, that person's wife does not just take that treatment. It is supposed to be only that person to whom that prescription was, for whom the prescription was written. So in an agricultural example, where say, for example, there are two side-by-side plots, and you give fertilizer in one plot, and in another plot, you do not give any fertilizer, and you want to see what is the effect of this fertilizer. But say, for example, if there was a rain and this fertilizer flows over to the other field where the fertilizer was not given originally, then whatever result we get out of that experiment will be violating the no interference assumption. Obviously, we do not want that. If we have a treatment group and we have a control group, we need to strictly maintain the situation that the treated group only gets the treatment and the control group does not get the treatment. Then we can estimate the treatment effect properly. So these are the 4 assumptions that we generally use to make an estimate out of this average treatment effect. And these scenarios will be applicable to a scenario where you are running a randomized clinical trial. But when you are moving on to a observational study, when there is no randomization, then we need to extend these assumptions, particularly this exchangeability assumption and this positivity assumption. So in that scenario, this extended assumptions would be that these exchangeability assumptions hold under certain L or the confounding condition. Say, for example, the older age and younger age example that I have given. If you think that age was the only determining factor for a patient to get the treatment or not, then you can still estimate the treatment effect if you simply divide the patients by age group, right? So for example, if we are only dealing with 15-year-olds, then if age is the determining factor, then we can simply do the experiment with only 15 years old to get the treatment effect within that 15-year-old population. Then there should not be any bias, because in our example, age was the only biasing factor or the confounding factor that was biasing the result. And then we estimate another population whose age are, say, for example, 55, and we get all of the participants whose age is 55, and we try to do this experiment of treated versus untreated within age 55, and then we still do not have any problem. But the problem begins when we try to mix up these 15-year-olds with the 55-year-olds. Then the problem begins. That's why we need to do a separate analysis, conditional on the confounding factor. So if age is the only determining factor that is creating all of this problem, then we can try to separate them out, make some sort of stratification, and then we can estimate these treatment effects separately. That is not a problem. But if we are averaging all of those separate estimates from 15 years old and that 55 years old, then the estimate might be biased. So separating out that actually solves the problem. All right, same goes for positivity. Remember, our previous definition was that in the positivity, the treatment effect, sorry, the probability of getting the treatment has to be bounded between 0 and 1. Now the assumption is extending whether within the, say, for example, 15-year-old, whether everybody's probability of getting the treatment is bounded between 0 and 1. Again, this would extend to the 55 years old as well. Within 55 years old, whether the probability of getting treatment is bounded between 0 and 1. So it cannot be exactly 0, it cannot be exactly 1, it has to be somewhere in between. So when we are moving from a randomized clinical trial scenario to a observational design, the only difference we are making is that we are conditioning with respect to the confounding variable that we believe is biasing the result of that observational design. All right, with that in mind, we are now extending our average treatment effect, but we are now extending to a scenario that we are interested in only one group of subjects. Let me explain. So in the scenario where you are trying to get the treatment effect for rosuvastatin, you may be interested to find out within the treated group, what did the patients look like? Say, for example, in the previous example that I was showing here, age was the only conditioning factor, and age was the only determining factor based on which our bias was being introduced in our analysis. Similarly, think of a scenario where we have more than one biasing factor. Say, for example, in our example, say, for example, this biasing factor or the confounding factor could be race, sex, and age. So these are the three confounding factors we know that exist in our analysis, and this is an observational data analysis. What we could do is we could try to find patients who have similar characteristic, and we can assign them in the placebo group, so that the characteristic that we have in the treated group and the characteristic that we have in the control group, they're all the same, right? So in our particular example, when we are talking about the relationship between the rosuvastatin and the cholesterol level, let us think of the scenario that we have 5 participants who were given rosuvastatin. All of them were white, all of them were male, and all of them were 50 years of age. So remember, we had this John, Jim, Jake, Cody, and Luke in our previous example. This time we are considering a more realistic scenario that we can only observe the outcome of these patients or the cholesterol level of these patients when these patients were all given the treatment or the rosuvastatin treatment. But we do not necessarily observe what would be the potential outcome when they did not take any rosuvastatin. So in our case, we cannot really estimate the treatment effect for the individual. So on an individual basis, I don't know what is the effect of this rosuvastatin on John. That I don't know, right? But the one thing that I know that all of these patients that I have share this characteristic that all of them are white, male, and 50 years of age, right? What I'm trying to do now is to find another group of patients, say for example, Jake, Justin, Cole, Lucas, and Dylan, who have exactly similar characteristic. They are all white, male, and 50 years of age. Exactly the same characteristic that the treated group patients had. But this time, I do not give these patients any treatment. So nobody got any rosuvastatin, they all got placebo. And then I follow them up, and at the end of the follow-up, I observe the potential outcome of these patients when they did not receive rosuvastatin. And I can simply average out the potential outcome when they did not receive the rosuvastatin. And I can also average out the potential outcome when the patients received rosuvastatin. And I can simply subtract these two quantities to get the average treatment effect on the treated. Now hold on, these are the average treatment effects. So why we are talking about average treatment effect on the treated? This is precisely because we are only interested in the treated group basically, because we want to see what is the effect of this treatment on this treated group. And we are trying to find another control group who looks very similar to the treated group so that we can make a apple-to-apple comparison, right? So in that scenario, we can see that the treated group is our reference group that we are primarily interested about. If that is the case, then we can estimate the ATT, or the average treatment effect on the treated, and that is basically the difference between the potential outcome from the treated group, the potential outcome from the control group, and we can simply get the average effect, right? So what would be the interpretation then? Remember, in the ATE, the interpretation was that everybody gets the treatment and everybody did not get that treatment. That was the interpretation for ATE. But the interpretation of ATT is that we want to get the average treatment effect from the treated population versus an untreated population, but that untreated population looks very similar to the treated population. So this is by design. We are trying to make the untreated population look like the treated population, because the treated population is the reference group here, right? And then we can estimate the average treatment effect, or ATT. And the nice thing about this ATT is that we can simply do some sort of matching to match the treated group with the untreated group to make the untreated group look very similar to the treated group, and we can estimate the treatment effect now. So remember, in the treatment effect on the individual, treatment effect on average treatment effect, both of them were hypothetical construct, right? We cannot necessarily observe the average treatment effect on from a group in a real world scenario, but in a real world scenario, in an observational study scenario, we can obviously estimate the ATT, right? So you can think of this scenario that ATT is basically some quantity that we can estimate from an observational design, whereas for ATE, we would need a randomized clinical trial or a time machine, whichever is possible to get the ATE. So generally speaking, when we have a randomized clinical trial, you would see no matter whether you are trying to estimate the ATT or ATE, both of the estimates will be similar. But if you have an observational study, then you will see the ATT and ATE are not necessarily the same. And particularly this is because there is some confounding factor that may be present in the observational data analysis. All right, let's move on to the next quantity, that is balance. What is a balance? So in a randomized clinical trial where you are trying to estimate the association between the treated group and a particular risk factor, what we do is we simply cross-tabulate the treatment with that particular risk factor. Say, for example, in our example, we have rosuvastatin and we have age groups, and these age groups are from 0 to 50, 50 to 70, and 70 plus. And we simply cross-tabulate them, and we try to figure out whether there is any imbalance. So what do I mean by balance versus imbalance? See, in this no rosuvastatin group, when the age was between 0 to 50, it was only 30.9% of the population who belongs to this group of no rosuvastatin and age group of 0 to 50. But when we move on to the rosuvastatin group, we can see 32% of the people belong to this rosuvastatin and the 0 to 50 years age group. And similarly, we can see 42% versus 43%, 26% versus 24% in the other age groups. What I'm really looking for is whether these percentages that we are seeing between these groups, whether they are comparable or not, right? So imagine a scenario where you are dealing with a large sample size and you are trying to estimate these numbers from this cross-tabulation of the treatment and the risk factor, and we see that 30 versus 32. I would generally say this is rather similar. 42 versus 43, again very similar. 26 versus 24, maybe similar. So in this scenario, I would say that we have balance in the covariate. So this age covariate is balanced between the no rosuvastatin versus the rosuvastatin group. So there is not a lot of difference in the percentages that we see with respect to this age. And this is generally a scenario what we see in a randomized clinical trial when there was some sort of randomization done for choosing who gets the rosuvastatin treatment versus who do not get the rosuvastatin treatment. And in that scenario, in a randomized clinical trial, we generally see this kind of balance. In an observational setting, however, when this age variable is not only a risk factor for Y, but also impacting the treatment decision, whether a doctor will prescribe you the rosuvastatin drug or not. In that scenario, we can see the proportion 63 versus 23, 26 versus 52, 11 versus 25. These proportions do not look the same with respect to this age category for both of these treated and untreated group. In that scenario, we would call that an imbalance. So that's how we are basically defining balance, whether the percentages that we see within the for a particular risk factor is similar within this two treatment group or not. If they're not similar, we are calling them as imbalance. But this is a rather very simplistic definition and does not necessarily have objectivity, because some people might still say, okay, we have still some difference. So what would be the cut point of the difference to call something as balanced versus imbalanced? To get a numerical measure of how to determine whether something is balanced versus imbalanced, we use something called standardized mean difference. And there are formulas for determining this standardized mean difference, and you can take a look at these formulas in the Austin's paper. And what this formula basically does is that if it is a continuous variable, it is basically a standardized mean difference. It is a mean difference, but we are also standardizing it. So we get some sort of estimate out of this standardized mean difference. So for example, for this age, we get a standardized mean difference, or SMD, as 0.89. So for example, we do the same for the smoking category. So I'm only showing the smoking yes category. There is also a smoking no category. But in the smoking yes category, you can see that this is the proportion 43 versus 54. And when we calculate the SMD, we get the 0.212. And similarly, there are other SMDs. So how do I really know which SMD is considered as balanced versus which SMD is considered as imbalanced? The general guideline is we use 0.1 as a cut point to determine whether a variable is balanced versus imbalanced. And we can see that every SMD that we are seeing here is above 0.1, so we would call them as imbalanced. So there is another measure that we use, it is known as variance ratio. And the general idea is that the variance that you get for the control group versus the treated group, the ratio of those variances should be close to 1. And we can go between 0.5 to 2 to determine whether there was any balance or not. But if there was a variance ratio that was below 0.5 or above 2, we would consider that as an imbalance. So these are the two measures that we generally use to determine whether there is balance in the two groups. One is the SMD, another is variance ratio. The first concept is why do we adjust? So for example, why do we run a regression or a matching or any kind of strategy to adjust for variable, right? Think of a scenario where you have a treatment effect, which is basically the difference between two quantities. If you have that treatment effect measured from an observational data analysis, that has two components. One component is that is really the treatment effect. The other component is that if there was any systematic difference between two groups, that systematic difference would also be included in that estimate that you get out of an observational study when there was no randomization. So for example, in our example, L was the age which was acting as a confounder. And the potential solution that we have suggested is that we can simply stratify this group. So for example, if you think that more than 50 years of old patients versus the less than 50 years of old patients are being treated differently, then simply calculate the treatment effect for the younger age, also treatment effect for the older age separately. And those separate treatment effects would be unbiased. So this is just one method. This stratification is just one method. We can also use other methods such as exact matching. We can simply match by what age was it? Was it 51? Then I would consider everyone in the population whose age was 51, and I would try to get the treatment effect for the age 51. But the problem is, if you have a variable that is continuous, such as age is a continuous variable, or if you have many different confounding factors, then what happens is that you have many different groups that you need to splice up this whole population. So at the end of it, you will have a lot of treatment effects for many different groups, and in each different group will have a very small number of sample size. And that is one problem for the exact matching. So regression is also a popular adjustment method where we can accommodate many different factors in our regression, and regression method is actually a very good method to address imbalance. So if there was some sort of imbalance in your data set where older age people were in the treated group more and the younger age people were in the control group more, then regression method would be the method that can actually handle this imbalance as well as many different covariates. What regression cannot adjust is the issue of non-overlap. Say, for example, if you have a scenario where you in your treatment group, you only have less than 50 years of old, and in the treated group, think of this scenario as if you have younger age population in the control group and if you have older age population only in the treated group, then actually there is no overlap for us to compare what was happening between one particular age group, because there is no one who got no one age group that got both of the treatment. And remember, one of our assumption was this positivity, that every person has to be eligible to get both of this treatment. That was the essence of the positivity assumption. But if we have this scenario that every older patients were treatment 50 and plus, and less than 50 were getting no treatment or the control, then we cannot really compare these two groups. And what we are doing when we are running regression in that scenario is that we are basically extrapolating, thinking that from that regression that we are running, what would have happened if those patients got the treatment versus no treatment. And this is the scenario where regression is basically making some sort of extrapolation to give you the treatment effect estimate result. But that result is not really reliable because you are not really having an overlap of the patients. So this is the scenario that can be explained in this scenario as well, that when this is the control group and this is the treated group, and you can compare both of these groups because there was some people who were not treated and some people who were treated in this particular green box. But say, for example, in this red box, some people were not treated, but there are no other comparators in the treated group. So that would be considered a scenario where we cannot really compare both of these treatment, right? So in this scenario, regression method would not be the method that can adjust this. And the problem with this regression method is that you would not even know that this was happening. You would just run the regression and you would get the results and go publish that result, but you probably would not even notice that this was happening in your dataset. So to remedy some of this problem, we will be talking about propensity score in the next section. So in this propensity score, now that we are already familiar with all of these different terminologies, hopefully we can move on a bit faster here. So in a propensity score context, we are using a slightly different example. And we are using this example to motivate our propensity score analysis. And we will also do a regression analysis at the end with the same problem. So our problem structure is slightly different. Our outcome is still the same, the cholesterol level. And we are kind of considering these high versus low cholesterol levels as the outcome, where this is yes and this is no, low is no. And we have a exposure variable, which is diabetes, whether a person has diabetes or not. And we have some known confounders such as gender, age, race, education, married, and BMI. So the question that we are really asking is this one, is that if you have diabetes, does it lead to high level of cholesterol? Is the question that we are trying to answer. You can also ask the question in a flip side as well, is that if you have high cholesterol, does that lead to diabetes, right? But we are asking the question in this certain way, that if you have diabetes, does it lead to high cholesterol? And we looked at the literature and we found out that there are some variables, say for example, gender variable, that impacts having diabetes, and gender variable can impact having different level of cholesterol. Same is happening. This is obviously a mistake. It should be income, BMI, marital status, education, race, and age. All of these variables are acting as a variable that is a risk factor for the disease, for the outcome, and also a risk factor for the exposure group. One key difference to note here is that we are not really using a treatment as an exposure variable. So here we are using a condition as an exposure variable, and that is an important distinction, that it is possible to get the effect of a condition rather than a treatment as well. Basically, we're interested to know whether having diabetes is impacting your cholesterol level or not, and we have identified some confounders from the literature. And to analyze this data, what we have done is that we have used the enhanced 2017-18 data. We have basically downloaded the enhanced data set. For those who are not familiar with enhanced, you can simply go to the enhanced website to see what are the components of the enhanced and what are the data and variables that you can collect from the enhanced website. So from that enhanced website, what we got is a cholesterol variable, even though it says numeric, but we only have two variables, two conditions, 0 and 1. So cholesterol is basically a binary variable. We have gender variable, which is a character variable, male, female. We have age variable. Age is a continuous variable. Race variable is a character variable, black, Hispanic, other, and white. Education variable, college, high school, school, married, never married, previously married. BMI is another variable. I think it is a continuous variable again. And diabetes, even though it says numeric, but it is basically a binary variable, whether you have diabetes or not, right? So basically we have this BMI variable and age variable that are continuous. Everything else is binary variable. So now we have a condition that we have an exposure variable A, we have an outcome variable Y, and we have a bunch of confounders that we need to adjust. Obviously, we could run a regression on it. That would be the easiest, but we are trying to learn first how to define a propensity score. So the formal definition of propensity score is that conditional probability of getting treatment given the observed covariates. So in our situation, we do not have any treatment, but we have a condition, diabetes. So in our situation, we would be, the propensity score would be conditional probability of being diabetic given the observed covariates, gender, age, race, and all of the other covariates that we have identified. So in a mathematical formula, you would see probability of being diabetic given age, gender, race, whatever covariates we have determined. So this L could be a multidimensional variable. That means that we could incorporate multiple factors in L. And the reason this propensity score works is because it was shown in a paper in 1983 by Rosenbaum and Rubin that if you have a sufficient list of confounders, say for example this L, and if you had adjusted this L to get the treatment effect for each of these conditions, that would be identical or similar to if you calculated this propensity score PS and if you conditioned your analysis based on this propensity scores, right? That is a powerful result. Let me explain why. Because in here, you have how many covariates? 1, 2, 3, 4, 5, 6, 6 covariates here at least. And what I'm trying to do is if I did a exact matching based on all of these 6 covariates, notice that age and income, I have not included income here. Age and income was not income. I think age and BMI. Age and BMI was continuous variables. And if I wanted to do exact matching with all of these covariates where we have 2 continuous variables, then it would not be possible for us to do any kind of exact matching, right? Think of this scenario. If we just split our data set into gender, we would have 2 treatment effect. Then if we subsplit that to age is a continuous variable, that would be infinite amount of subgrouping that was happening in our data set then. Even if we make some subgrouping, some categorization of the age, say for example, 5-year interval, even then we would have a lot of categories, and in each category, our sample size would be very low. Instead, what we are trying to do is we are using all of these variables to calculate this probability based on whether that person was exposed or not. So that would be just one variable. Instead of all of these 6, 7 variables, I would have just one variable. And what this theorem is saying, that instead of adjusting for all of these covariates that you may have, you can simply adjust for this propensity score. And that would give you the same level of comparison. So the results would be comparable. And the nice thing about this propensity score analysis is that now you have to adjust for only one covariate instead of all of the other covariates. So that is the essence of the propensity score that I am trying to convert. It's basically a dimension reduction exercise where I have many covariates. I'm basically compressing all of this information into one variable. And then I'm trying to determine whether I can make this comparison of the treated group and control group based on this propensity score only. I do not have to adjust for age, sex, and all of these other variables anymore. I just have to adjust for this propensity score. All right. For this propensity score, the way this propensity score was derived, I still need this conditional exchangeability, conditional positivity, and consistency assumption. Again, once more, the reminder is that within a particular subgroup, I need to have a scenario where there was no bias. So for example, in our previous example, we said that if we condition on age, only younger age, then we do not have any bias in our result. Similarly, we are now saying that if we condition instead of AL, if we condition on certain PS variable, and we try to compare these 2 individuals that has certain propensity score, then they are comparable. So for example, there are 2 persons with propensity score 0.8. One person is in the treated group and one person is in the control group. We can still make a comparison of these 2 because both of them share the propensity score of 0.8. So we can say both of these people are comparable. Similarly, we need the assumption of positivity. The propensity score cannot be exactly 0, cannot be exactly 1. It has to be somewhere in between. And the consistency assumption is still the same. For the treatment for which we are defining this, propensity score, diabetic, we need only diabetic patients. We cannot simply mix all of these other comorbid conditions here. We simply need a precise definition of diabetes for this definition to work. All right. See, propensity score is a probability. And because this is a probability, it has to vary between 0 to 1. So it has to be bounded between 0 to 1. All right. So in the next stage, I will show you what are the ways to calculate propensity score, but know that there are many different ways we can use propensity score in our analysis. One is matching, weighting, stratification, and we can also use propensity score as a covariate in the regression. But for our purpose, for our workshop today, I am just going to explain the propensity score matching. Once you understand the propensity score matching, there is a it is a clear transition from understanding propensity score matching to propensity score weighting. So once you understand propensity score matching, you can read further materials to understand what is propensity weighting, stratification, and covariate. But let me start with this propensity score matching. And I'm following the guideline from the Austin's paper here from 2011, who proposed 4 different steps of doing propensity score analysis. And in the next few chapters, I'm going to explain one by one what are these steps mean and what do they do. But in summary, the way propensity score works is that at first I try to model the exposure. See, generally speaking, when we are estimating treatment effect, we try to have outcome model where outcome or y is the on the left-hand side of the equation. But in here, we are doing exposure modeling. This is not outcome modeling. This is exposure modeling. And that's why we have this exposure condition on the left-hand side of the equation. Once we feed the propensity score model, we try to estimate the probability from the propensity score model to get the propensity scores. That is our first step. In the second step, once we estimate the propensity score, we try to match by the propensity score. So we try to see, say, for example, if one person in the treated group is 0.8, can we find a similar propensity score in the control group so that we can call those propensity scores as similar? Once we do all of this matching, we have a reduced sample size. And in that reduced sample size, we want to see the balance and overlap. Remember some of the concepts we discussed in our chapter 2, balance and overlap? We are going to assess them in our step 3. And in our step 4, we are basically going to check the outcome modeling. So we are basically going to estimate the probability or estimate the effect of treatment on the outcome. And in this case, y would be in our left-hand side of the equation. Any questions so far about the propensity score? Hearing none, let me start with the first step. So in the first step, what do we do? If you have any question, feel free to post them in the chat box as well. I'm happy to answer them in the next time I pause. So as we have seen, the propensity score is basically probability of being exposed given the observed treatments. So A, or the exposure variable, is on the left-hand side, and on the right-hand side, we have the confounder variables. So basically what we are trying to do is diabetes is on the left-hand side, and all of these covariates is on the right-hand side. That is how we are going to model this. All right. So remember this diabetes variable that we were dealing with? This diabetes variable was a binary variable. It had just 0 and 1. That means either you have diabetes or you do not have diabetes. And when we have a binary variable, we try to run logistic regression to get the estimates from that regression. So we basically have a binary variable as the outcome, and we have all of these confounding variable. And we define the propensity score formula, and we try to simply run a logistic regression. We can use any software. I'm just showing it in R, but you can use any possible software to run a logistic regression model with this formulation, right? And in this logistic regression, you will see, obviously, you can print out the outcome of the logistic regression, and you can see all of these coefficients and whatnot. But interestingly, for the propensity score analysis, I do not necessarily care about these coefficients that I get out of a logistic regression model. So the coefficients of the propensity score model is not really a concern, and we can make the model rich. So what does that mean? That means that in my propensity score model, if I wanted, I could have included the interaction between some of the variables that are biologically plausible. So for example, I could have made an interaction between the education variable and the BMI variable. That is possible. Also, if I thought that age is a variable that has nonlinear patterns, I could have included polynomial terms. That means that I could have used age, age square, age cube in the same equation. Generally speaking, out of the concern of the parameter to be estimated, if we have less amount of data and more parameter to be estimated in the outcome model, this is a concern if you are using too many parameters. So once you have included a list of confounders, each of these confounders would include one parameter with each confounders. And then when you include a interaction term, that would introduce another parameter. When you introduce a polynomial term, age square, that would increase the number of parameters. But generally speaking, in the propensity score model, I do not necessarily think that you need to be restricted. You can make your model rich. Right. So one question that I received in a private message is that, is there a restriction on the number of covariates that are included to calculate the propensity score? Generally speaking, obviously, if you have more parameters to estimate compared to the data set that you have, that would be a problem. Then you cannot really estimate the parameters in a way when the parameters would be stable. So given your data set, if your data set is large, then you can use more covariates and more parameters and all of that to estimate the stable parameters. But generally speaking, if you have a small amount of data, then you need to be careful about which parameters or which number of covariates you need to include. So again, there is a balance between how many parameters you want to include or the covariates you want to include versus the how much data that you have. All right, so even though I'm not really interested about the coefficients, one thing I'm interested about is the standard errors. If you generally see any of these standard errors are very large, and by very large, I mean by thousands or even more than that, then it might be an indication that there is some collinearity going on in your data set, and you need to take some measures of either deleting some of the variables that are highly collinear to get rid of that problem. All right. So the one general question that I often get is, what type of variable should I adjust? So for example, when I'm getting access to enhanced data has a lot of covariates, right? And how many covariates or which covariates should I include in my propensity score? So there is a general guideline about which variables to be included in the propensity score model. And the most obvious one is the one that is known as a confounder. That is something that causes outcome and causes the exposure. Say, for example, if you think age is a confounder that is impacting your cholesterol level as well as your possibility of getting diabetes, then obviously age is a confounder. But even if you can find some of the variables that are only causing the outcome, those variables are also good to reduce the standard error of the treatment effect estimate that you get. The variables that are instruments, that means that are only causing your exposure variable, and then that exposure variable is causing your Y. Those are known as the instrumental variables, and instrumental variables should not be included in the model because then the standard error will amplify. And also, most importantly, and this is why it is very important to determine the baseline of any study, is that if you have a mediating factor, that means that if I have diabetes and diabetes is leading you to not do any kind of physical exercise, and then that not doing physical exercise is impacting your cholesterol level, then that would be a mediator. And you should not adjust for any mediator variable in your analysis. And generally speaking, it is a very good idea to have a strict baseline in your study and also try to draw a causal diagram so that you can try to rationalize why you are including a variable in the analysis. Just because you have access to a variable does not necessarily mean that you should include that variable in the analysis. All right, before I move on, there was one question: which technique of propensity score is most preferred or has more advantages than others? If you are talking about preferred, matching is the most preferred technique, and that part I will discuss at the guideline section. And if you are talking about advantages, it kind of depends on which type of estimate that you are trying to get. Say, for example, if you are interested about, say, for example, this particular question, diabetes, whether it is causing someone to have more cholesterol or not, then you are basically interested about diabetes patients. Diabetes patients are your reference group, right? You are not necessarily interested about the patients who do not have diabetes, right? So in that case, average treatment effect for the treated or for the people who have diabetes is of interest for you. And then matching is the method that would give you the ATT. But if you are for some reason interested about both of these groups, you are not only interested about diabetes, you are also interested about non-diabetic patients, and you are interested to estimate the ATE, then weighting methods could be helpful. So there are many other different reasons for you to choose another method, and hopefully I will also talk about that in the guidelines section later on. All right, coming back to this point, when we have covariates, and we have a lot of covariates, sometimes you will see in the literature people do some sort of stepwise regression, and that stepwise regression could be p-value based or the criterion based to determine the optimal model for the propensity score model. If you have a problem with the sample size or anything like that, try to determine whether to include a variable or not based on your subject area knowledge, whether age variable should be included or sex variable should be included or other variables. The stepwise regression methods are not generally recommended for model selection when we are trying to make a causal interpretation out of a model. Stepwise models are generally discouraged. If you have a problem of how to select a variable and which variable to select, talk with the subject area expert who knows about the process of diabetes and this process of cholesterol level increase. They may be able to lead you to the direction of which variable to include. Do not use these stepwise type of methods to do any kind of variable selection. All right, generally speaking, one other thing that you probably would want to do is you do not want to calculate which variables to include in your data based on the outcome data. So for example, you have the cholesterol data, you can try to see the correlation between this cholesterol data and the other variable, say for example, age data, and you then try to determine whether this age variable should be included in your model or not. For a propensity score analysis perspective, that is usually discouraged, because that's why we have two stages, at least two stages of different modeling. One stage is step 1, propensity score model is, and another stage is stage 4, where we do the outcome modeling. So we keep the outcome separate from the step 1. So generally, calculating this correlation and determining which variables to include in your model, in the propensity score model, is discouraged. But then again, there are some other issues, such as you cannot always have subject area expertise on all of the topics of interest. That means that, say for example, there is a variable, marriage variable, say for example, and you talked with many other experts, and you do not necessarily get a consensus on whether this marriage variable is really a confounder or not. And from the previous subject area expertise or the literature, you do not have a sense of whether this variable is important or not. So sometimes that may be justifiable if you do not have a subject area expertise in that. But generally speaking, if you can have some sort of subject area expertise, try to lean on that to try to figure out which variables to include in your propensity score model. Especially this is important because we are trying to do some sort of causal interpretation of the estimates that we are getting. So it is always advisable to draw a DAG like this, and once you draw that DAG, then you can have a better sense of which variables to include in your model. All right, so far we have talked about only the variables to be included. We did not really talk about too much about the model specification. So what are the components of model specification? Model specification is not only about which variables you include, but also in which form you include, right? What that means is, say for example, you have all of these variables, but you are simply adding all of these variables, right? There is no square term, there is no interaction term, or no polynomial term, no cubic terms. So we are just adding this term, but we do not necessarily know whether this simple addition is the right formula to determine the risk of diabetes or probability of being exposed to diabetes, right? So it could be there is a complex formula. It could be age square. It could be an interaction between this education and BMI and all of that, right? So there could be a more complex formulation that you may need. But the problem with the real data analysis is that we do not necessarily know what is the real formula we should use because we do not necessarily have that kind of detailed information. So for that, you may be able to use some sort of machine learning methods that are very well adapted to deal with nonlinearity and non-additivity. And I'm going to show you one particular example of machine learning method later on. So those could be also used as an alternative strategy to estimate the propensity score. So not only the logistic regression that you have to use in your propensity score model, you can also use many other different machine learning methods or the nonlinear, non-parametric methods to estimate the probabilities of getting exposed, which is the propensity scores. So propensity score method does not really dictate which particular method you need to use to get the propensity score. All you need is a method that can estimate the probability of getting exposed or getting treated. All right. So you can simply get the predicted values of getting treated out of whatever method you fit. It could be logistic regression, it could be other machine learning methods. And once you get the predicted values, those predicted values are the propensity scores. It is that simple. You fit a exposure model with a bunch of covariates with some potentially interaction terms and polynomial terms, and then you predict them. And these predicted values are the propensity scores. And in our data set, we simply fitted the logistic model to get the predictions, and we simply plotted this density plot using those predicted values, which are the propensity scores. And you can see the red line is, or the red color is for the non-treated, and blue color is for the treated. And you can see mostly there are some overlaps. There are some non-overlap maybe here, and there's some non-overlap maybe here. But generally speaking, in most of these scenarios, you can see there is an overlap. So this is the part we are again going to investigate a bit more further in the step 2. So far we have, the only thing that we have done is exposure modeling. And the main message of this exposure modeling is that we need to formulate a model to predict the exposure variable that you have. And then we get the predicted values from that fit, and that predicted values are the propensity scores. And that is the stage 1 or the step 1 for our propensity score matching. Do you have any question before I move on to the step 2? All right, there is one question. When the aim of the study was to estimate the direct effect of the treatment example, can I introduce mediating factor in the propensity score model? All right, mediation analysis is something actually different. So when you are interested particularly about the mediation part, that means that you are interested about dissecting the total effect into the direct effect and the indirect effect. And the particular propensity score matching technique that I'm showing today is more geared towards total effect. So I'm not necessarily using the methods that I'm going to show today is not necessarily dealing with the direct effect or the mediation effect. So the general guideline for this type of propensity score, when you are aiming to just fit the to get the total effect, then we simply do not adjust for the mediating factors. All right, so in the step 2, what we are going to do is that now we have these propensity scores, right? We have all of these propensity scores, and these propensity scores, as if you can remember, these propensity scores vary from 0 to 1, right? And consider a scenario where you have a propensity score for a treated person with 0.25. So you can also find another person with a propensity score of 0.2 from the control group, but 0.25 from the control group, but we are dealing with a continuous variable here, right? So we cannot really do exact matching, because if we did exact matching, we could not match anybody, or the amount of matching would be very small, even if we round it. So one technique that we use, and that is the step 2 of propensity score matching, is to use a matching algorithm to match the treated people and the untreated people. And one of the most popular matching algorithm is known as the nearest neighborhood matching. And what this nearest neighborhood matching does is that, say, for example, these blue lines are the treated and these red lines are the untreated. So what this nearest neighborhood matching algorithm will try to do is to try to match the treated people with the untreated people, and it will try to match with the untreated people who is the closest. So say, for example, in this particular example, you can see this red line and this red line, both of them are almost at the same distance from the treated person here. So in that scenario, what the propensity score matching algorithm or the nearest neighborhood matching algorithm would do is it will at random select a person from the from this pool of untreated patients. So it is very important to set the randomization seed so that you can get replications at the end of your analysis. The other idea is that, say, for example, you have this person who is untreated, sorry, who is treated, and you are trying to figure out which person you should fit or match with this treated person, which untreated person you should match with this treated person. And if you have this person still available who is not already matched with someone else, then you can simply match this person. Or if this person is already matched with this other treated group, then you still have available this person. So you can simply match these people. So this algorithm allows you to match with replacement or without replacement. That means that if you match with replacement, that means that you can select the same control for the two different treated person. But if you are using the without replacement, that means that once these two persons are matched, then you need to choose another different person to match with this new untreated person, right? The third idea of this is the caliper. That means that you have to have a radius. You cannot simply match this person with this person just because nobody else is available. If the distance between the propensity scores are very high, then we do not match this person. We simply delete this person if there is no match within certain radius, right? And we can also try to do 1-to-1 ratio matching or 1-to-5 ratio matching or something like that. That means that you can try to have the one treated person and at least one control person. Or if you are using 1-to-3 matching ratio, then for one treated person, you need to find 3 control person and so on. So in this matching algorithm, what we are trying to do is we are trying to match the person who is most closest to you. And that's why we are calling this as a nearest neighborhood matching. So generally speaking, there is a guideline that when you are choosing the radius beyond which you should not match is known as caliper. And this caliper has to be the 0.2 standard deviation of the logit of the propensity score. And that means what? You need to first fit a propensity score model, and then you get the logit of the propensity score, take the standard deviation and take the 0.2 to get the caliper, and then you refit the propensity score model. So if you are using this caliper, then you have to do it in 2 stages. So let me show it in a step-by-step basis. So initially, when we fit the propensity score model, and this propensity score model, I'm fitting it in R, but you can use SAS or other softwares to fit the nearest neighborhood matching approach is very popular and available in many different examples, in many different softwares. So we are using the nearest neighborhood matching. We're setting replace equals false. That means that we are doing without replacement here. And we are also doing a 1-to-1 ratio. And for that, we simply need to mention ratio equal to 1, right? So in R, we are using this match it package and using this match it function to get the matching. And look at this summary object that we are finding, that initially we had 1,562 patients, but after 1-to-1 matching, we only have 660 matched subjects, right? That means that we are deleting more than half of the patients to get the people who are matched, right? See that in this initial matching, there is no caliper that we are using. All right. So now that we have estimated, we have matched the first initial fit, we can also estimate the propensity scores from that fit. And those propensity scores, see, all of them are between 0 and 1. And we can use this initial fit of the propensity score to determine the 0.2 standard deviation of the logit of propensity scores. And we can use this as a caliper for the next fit. So we did an initial fit to get an initial value of the propensity scores, and then we did a caliper estimation, and we use this caliper estimation to calculate the propensity scores again. See, from the original population, we had 1,562, and now we have 632 matched subjects. And then because we are doing a matching, we are getting the ATT as the target estimate. And we are using all of these covariates to estimate the propensity scores. And you can also take a look at the matches. Say, for example, the person whose ID was 40 in the treated group, he was matched with a person with the ID of 8495 in the control group, and so on. You can try to see that from the analysis as well. Although it's not necessary for you to see, it's just a way to demonstrate you what is happening. One treated unit was matched with only one control unit, and one treated unit was matched with only one control unit. Sometimes you get this notification that there are some patients who could not be matched. That means that for some treated patients, nobody could be found within that caliper from the control patients, so we could not match them. And this nearest neighborhood matching is popular, but not the only method. There are other methods like variable ratio nearest neighborhood matching, CM method, generating matching, and optimal matching. I'm not going to discuss about them. Generally speaking, the nearest neighborhood matching is the most popular method that people generally use. So this is the end of our step 2. In step 3, when we did, in the first step, we estimated the propensity scores. In the second step, we matched the population using those estimated propensity scores, right? So the third step is assessing the balance in the matched data set. Remember, there are two concepts we discussed. One was this standardized mean difference, and another was variance ratio. We are just going to use those as well as some visualization techniques to get the understanding of the balance and lack of overlap in the step 3. So in the step 3, what we are doing is trying to use the SMD values to get an understanding of what is the balance. So before I do it with the matched data, let me do it with the full data. In the full data, look at the SMDs that we were getting. Remember, the cut point that we are using for the SMD is 0.1. So basically what we see here is that almost all of these variables, actually all of these variables have SMD that are greater than 0.1. So by our definition, we would say all of these variables that we are using, such as this BMI, married, education, and all of these variables, those were imbalanced to begin with in the full data. But let us see what happens after we have matched the data. And after matching the data, these are the new SMDs that we are getting. And remember, our cut point was 0.1, right? So by that definition, you can see only race variable had a SMD of 0.105, right? So barely above the cut point. So you can make a judgment whether you consider this as imbalance, or you want to refit your model, or try to get a sense of how to reduce this SMD. So the general idea is that if you have fitted propensity score model, matched your data, and estimated this SMD, and still getting SMD greater than 0.1, the general idea is that you refit your model. So you go back in your step 1 and you change your model specification, maybe include some polynomial, maybe include some interaction term, or maybe include some other covariates, and then try to refit and come back to this SMD and try to see whether you have been able to reduce the standardized mean difference. One particular point I want to mention is that generally speaking, when you are stratifying the variables with respect to the exposure variable, you can also calculate the p-values. And the general understanding is that if the p-value is less than 0.05, then you say that there is some imbalance. But if the p-value is greater than 0.05, then you say that there is balance, because there is no difference in these two groups. But the problem with this p-value is that p-value is impacted by the sample size, whereas this SMD is not impacted by the sample size. And that is why SMDs are preferable to the p-values. Let me show you one example, one recent example using this COVID example, or the COVID paper that was published last year, where they stratified the exposure group with respect to all of these COVID rates, and they calculated the p-values. And just because all of these p-values were greater than 0.05, they said that all of these groups are balanced. But this example used a sample size of, if I remember correctly, 300 or something like that. Oh, sorry, 54 or something like that. And that was a relatively low sample size. And those sample sizes were driving these p-values to be higher. But if I calculated the SMD, I can see at least one SMD was less than 0.1 cut point that we are defining now. That means with respect to calculating the SMD, we would find imbalance, whereas when we are using the p-values, we are not finding any imbalance. So you see a practical example where SMD was superior in determining the imbalance. And you can find this example in this particular paper. There is a reference list at the end of this teaching material. All right, we talked about balance. Now let's talk about overlap. How do we determine overlap? We can either draw a box plot, or we can try to find which are the matched unit and which are the control units. See, these are the matched unit, these are the matched control units, these are the untreated, unmatched treated unit, unmatched control units. But to get a better understanding, I think histogram is generally a better way of finding whether there is enough balance. So, sorry, enough overlap in the treated unit and the control unit. See, all of these are going from 0 to 1, 0 to 1. There is no gap. That's why we are saying that there is no overlap. All right, similarly, we can try to estimate the variance ratio, and we can try to see whether the variance ratio is between 0.1 to 2. The ideal would be 1. And we can calculate the variance ratios, and we can try to see whether the variance ratios are greater than 2, none of them are. Whether the variance ratios are less than 0.5, none of them are. So we say that even in terms of the variance ratio, we are good. So in terms of SMD, we were good with, except the raise variable. Raise variable was 0.105, right? All right. And we can do some other closer inspection of whether they were very close to 1 and very close to 0 or not. These are very good visualization technique to identify whether there was any positivity problem or not. All right, so that brings us to the last step. So we have done the propensity score modeling. We have matched the propensity scores, and we have checked the overlap and the balance criteria in the matched data sets. So once we are happy with the third step, that means that once we are happy that the balance was good enough, or there was no problem with the overlap of the propensity scores, then only we move on to this step 4, right? So in the step 4, there are different ways you can calculate the outcome modeling. And one thing to remember here is that in the step 4, we are only dealing with the matched data. We're not dealing with the whole population. We have matched our propensity scores to get the matched data. And in this matched data, we can try to estimate the relationship between the cholesterol and diabetes, right? And we we estimated that in a crude model, and the odds ratio was 0.9. There is one other method that people generally propose is called the double adjustment method. That means that whichever variable was found to be imbalanced, you just adjust that variable in the outcome model, and that gives us the odds ratio of 0.89, which is very close to the true odds ratio, the odds ratio that we got from the crude. We can also do a adjusted outcome. That means that whichever variables that you feel are confounders for the diabetic and cholesterol level association, you can adjust for all of these variables, and you can get the odds ratio of 0.86. The general understanding is that we do the propensity score model in two different stages because we want to keep them separate. And if we feel that some confounder variable is present, we should adjust for them in the treated exposure modeling as well as in the outcome modeling to get rid of all kind of confounding. Even if we adjusted all of these variables in the outcome modeling, in the matched data, we can see our odds ratios are very similar to the one that we got in the crude model. Right? There are one other consideration is that, remember, we are using this matched data. That means that this person in the treated group and the control group, everyone is matched with respect to propensity score. So that means we are dealing with a scenario, we have done some sort of matching. And when we do some sort of matching and we try to get the estimate, the one problem is that the confidence intervals are not reliable anymore because we are not taking into account of the clustering that is happening or the matching that, that has happened in the data. So to remedy that problem, the general suggestion is used to cluster option or take into account of the matching in your analysis. That means that you need to estimate the robust standard error from the analysis. And if you estimate the robust standard error, the estimate of the odds ratio will not change. The confidence intervals might be slightly different compared to the before. People can use Bootstrap, but generally speaking, when you are using without replacement, then Bootstrap is good. Remember, in the step 2, we were using without replacement in the nearest neighborhood matching. If we are using without replacement, we can use Bootstrap, but if we use the with replacement, then Bootstrap might not be the most appropriate. All right. So now think about the interpretation. What is the interpretation of all of this? The interpretation is that since we are getting the odds ratio from a matched data set, we are getting the ATT interpretation of this treatment effect. Any questions so far? None? Okay. So one, in matching and balance step, we are disregarding the observations who are not matched or balanced. Will that problem? Yeah, I mean, obviously, one problem is that if you are disregarding a lot of the different patients, and I'm going to talk about this slightly later, is that if you have deleted many different people and you are reducing your sample size, there should be problem in the analysis. But then again, in your outcome analysis, see, for example, when you did the crude outcome analysis, your results did not really vary that much compared to the adjusted analysis. So that means that there is less parameterization in the outcome analysis. So in that sense, you are still somewhat safer, even if you are reducing a lot of sample sizes. All right, one example I want to quickly show in terms of what is the difference between the propensity score matching and the regression. And for that, because I need to know what is the true parameter, I need to design a simulation study. I cannot really rely on the observational data analysis to know that. So we are using the same example of the diabetes and cholesterol to simulate the data. And one particular aspect that I want you to see is that when I estimate the treatment effect from a conditional model where L was a confounder. And I was generally interested about a scenario where my treatment effect was 0.7. So in our simulation, the way we have designed our simulation, our treatment effect was 0.7. And when we used a regression analysis after adjusting for L, our treatment effect was still very close to 0.71, 0.7, which is 0.71. All right, so that is coming from a regression. When we did the propensity score analysis, we also get an estimate of 0.71. That means what? When we are doing regression and when we are doing propensity score estimation, we are getting very similar estimates. And the bias level was very minimal when we have adequate sample size. So why would anyone want to do this propensity score matching with 4 different steps where we can simply use regression method in 1 step, right? So that is a very general question that you can have, like, why would anyone consider doing 4 steps instead of 1 step? So let me show you just one example where I have again generated the data in the same way as before, but this time I have included a cubic term. Say, for example, if L is age variable, I'm just using a cubic term to determine the outcome, right? So that means that there is a non-linearity present in the data generation process. Obviously, we cannot know this true data generating mechanism ever, but if the data was generated in this way, look at the results. So when we did our regression, our true parameter was still 0.7, but we were getting a very different estimate now, right? 0.7 versus -2, very different. But when we estimated the propensity score, we get 0.67 compared to 0.7, which is very close, right? So that means that when we have any sort of non-linearity in the data generating process, then matching method is more robust compared to a regression method. And we can also use machine learning methods, such as I'm using a gradient boosting method in here to estimate the propensity score, because these methods are very adaptable and can accommodate any kind of nonlinear functions. And then when I estimated the propensity scores, the propensity score estimate and got the treatment effect, and the treatment effect estimate was 0.72 compared to 0.7. That means when I'm using regular propensity score using logistic regression, when I'm using machine learning method to estimate propensity score, both of them are giving me estimate of 0.67 and 0.72, which is very close to the true estimate of 0.7. So the main message that I want to convey here is that when we are dealing with real data analysis and we do not have an understanding of what is the real data generation mechanism, propensity score method is more robust compared to a regression method that can give you a better estimate. And obviously, machine learning methods can also help in determining good estimates in that sense as well. So what does that mean? Regression method should not be used at all? Not really. I mean, it is always a good idea to check the diagnostic plots of regression. And if you look at the diagnostic plot of the regression, you will see there was a curvature pattern in the residual plot. Residual plots are supposed to be any kind of trend free, but I can see a trend here. So that means that I should have adjusted my regression model to get a better estimate or a reliable estimate. All right, so I think in terms of the general guideline, there are a couple of different things that you need to report in the article when you are writing an article about the propensity score analysis. And the first part of this is which particular population you are using. Are you particularly concerned about the diabetes patient or all patients? And that will determine which type of analysis you need to use. So if you are using ATT, you would only get the reference group of diabetes patients who are of main focus of interest. But if that is not the case, if you are interested in finding the overall population as the reference, then ATE method would be more appropriate, and then you would have to use the weighting method. Remember, in the intervention, there was this consistency assumption of no multiple version of treatment and all that. Those part needs to be clearly explained. Why do you think there was no multiple version of the treatment? In terms of the covariate, you need to be very clear why particular covariate list was chosen, which of the covariate list was included, whether you have included any proxy variables if you had not had access to the original covariate. You also need to report what propensity score model you have used to build the propensity score model, whether it is logistic or machine learning, or what type of specification you have used. You need to justify why you are using matching. You need to report how many data sets you have deleted. And most importantly, you have to report the step 3 materials, like whether there was any overlap or balance issues. And also, sometimes people do some sensitivity analysis. It is also good to report on this sensitivity analysis. And there are some additional issues that I did not really touch on, like subgroup analysis and missing data. Those should be also reported, like how you have used those in your analysis. And the final comment that I just want to make quickly is that there is a general misconception that whenever you are using propensity score, you are getting some sort of causal result. And when you are using regression, you are getting some sort of associational measure. This is not true. In both of these cases, if you are not carefully designing the analysis, you are getting some sort of association measures. If you need to make some causal interpretation out of your result, you need to establish causality, and established causality requires many different points, such as establishing temporality or integration of the subject area expertise. So those should be taken into account. So why would someone use propensity score? So this is the general question, and the main idea is that this is intuitive. You can explain this idea of matching to any doctors without any statistical expertise. This is a two-step process. That means that you are explicitly thinking about the treatment or the exposure generating process, as well as explicitly thinking about the outcome generation process, right? So that gives you two chances of thinking about the model carefully. If you have a rich propensity score model, then you can use machine learning methods to bypass some of the strict assumptions that we generally make when you are using the logistic regression model to fit the propensity score. And of course, this reduced dimension, that means that it is, if you are using propensity score, you are obviously reducing all of these covariates into one variable that is useful to do the analysis. And also these diagnostics plots that you are using from a propensity score model analysis, that is much easier compared to a regression analysis that you generally check. But there are obvious problems of propensity score. That means that when you are matching and you are deleting a lot of subjects, then sometimes the target population can be different than the original population that you intended. And you have to be very careful about deleting a lot of, if you are deleting a lot of patients, maybe think about your propensity score model a bit further. There are many different software that you can use, and I'm listing some R software. Other than R software, there are many SAS, data, SPSS packages. You can get a list of those packages from Elizabeth Stewart's page. If you're interested about further learning about propensity scores and other approaches such as weighting and all of these, I have a workshop page set up that includes the material from my previous workshops as well as some of the videos. You can try to check them. I have a YouTube channel where I have uploaded some of the teaching materials I have, so you can take a look at those. Some of the teaching web apps that I have developed, you can take a look at those as well. So with that in mind, I'm concluding this workshop.